Now we're going to talk about the gradient operation in curvilinear coordinates, but before we do that, I want to recall the physical picture of the gradient. If you remember, the gradient of a scalar field is a vector that describes the change in field at each position, so that when I take the dot product of the gradient with a displacement vector, I would get the change in that scalar field. So if a displacement is perpendicular to the gradient, that means the change is going to be zero. In other words, gradient always points perpendicular to constant phi surfaces. Now let's take a look at this definition again. The change in the scalar field phi is gradient of phi dot product with the displacement. So we're going to take a dot product with the gradient of phi dot product with the displacement dr. This is going to give us the change in the scalar field. Now the displacement we have found in curvilinear coordinates is given by del r j del qj, the change of the position vector with the coordinate qj dqj, which is equal to the scale factor hj qj hat times dqj. So hj dqj in qj hat direction. So the unit vector in the on the qj coordinate axis. Now we have also a change in scalar function given by differential calculus as the partial derivative of the scalar field phi with respect to qi multiplied with dqi. So we can put this together. So this is the meaning of a differential change in the scalar function phi. Phi is a function of q1, q2, q3. So for each variable in the function, we have to take the partial derivative and multiply it with the differential change in that variable. So this tells us that del phi del qi dqi it must be equal to the gradient of phi. So we have the gradient of phi dot product with the displacement vector. The displacement vector written in curvilinear coordinates del dqj hj scale factor in qj hat direction. So now putting this together, I have to take a dot product of a vector with qj hat. It will give me the ith component. That's telling me that gradient of phi must be in qi hat direction. And on the other hand, the scalar product will turn I equal to j, so dqi's will cancel. So I will have 1 over hi del phi del qi. So you can see from this equation, you can read from this equation that the gradient of the scalar field phi is given by, we can now substitute the result, 1 over hi, the scale factor, the partial derivative of the scalar function, scalar field phi, with respect to qi del phi del qi, and this must be in qi hat direction. So once again, when I take the dot product, qi hat qj hat gives me delta ij. So this I will turn into j, hj's will cancel, and I will have del phi del qj dqj, which is going to be equal to d phi. Or we can substitute I for j, it's the same thing. So we have reached the final answer for the gradient of a scalar field written in curvilinear coordinates. So what we have to do is to take the partial derivative with respect to that coordinate in this curvilinear coordinate system, multiply it with the unit vector in that direction, and also we have to divide it by the scale factor. So we have gone through the gradient in a curvilinear coordinate system by using the definition of the gradient. D phi is equal to gradient of phi dot dr, and we know that if a displacement is perpendicular, if we are on a constant phi surface, the gradient will be perpendicular to that surface. So that's basically what we have recalled here. If we go back, so we can see that the gradient always perpendicular to constant phi surfaces, and we can use the differential calculus definition of the differential change in phi, which is you have to take the partial derivatives with respect to all variables and multiply it by a differential change in that variable and add it up. So this is an addition process. And for the small displacement, differential displacement, we have our previous result, which is a scale factor times dqj qj hat. So we can put it together, and this gives us our final answer for the gradient of a scalar field phi as 1 over hi del phi del qi in qi hat direction.